Welcome to the Math Record. Today we'll be covering the first video for our whatever class. In this class, we'll just be teaching anything we like that we think is interesting. For this video, we'll be deriving formulas for summations of polynomials over exponentials, which we will split into two videos. For just this video, we'll be introducing the idea on the second, and on the second, we'll be extending the idea for higher level polynomials. Okay, so what we need to know first is for these summations to work, it has to be an infinite geometric series. So what I mean is that if we have like a sequence, like 1 over 5, and 1 over 25, 1 over 125, 1 over 625, then it's infinitely geometric because the ratio is between -1 and 1. So it's 1 over 5 times 1 over 5 is 1 over 25. 1 over 25 times 1 over 5 is 125. 1 over 125, and 1 over 125 times 1 over 5 is 1 over 625, right? So the ratio has to be between -1 and 1 for it to be infinitely geometric. Because as we go on to infinity, the number has to decrease and get smaller. So as it gets smaller, if we add those number up, it should converge to a single number. Unless, and that's why it doesn't work for a finite for a regular geometric series. Because if it's something like 5, 10, and then 20, and then 40, and then like 80, right? It goes up by scale factor of 2. So 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, 40 times 2 is 80, right? So that will infinitely get bigger. So as that big get bigger, that means the sum would diverge because the number would be really big. So what it kind of looks like graphically is that if we have it infinitely geometric, it'll look something like this. While we have something that's geometric, it'll look something like this. So we could find the area of this. We just cannot find the area of this because this one's getting bigger over time, while this is getting smaller. But this is not taking integrals. So for this is just taking, if we're finding an area under a graph, that's taking an integral, which we won't be covering on this video, which we did cover in our calculus class. But what we're going to do is that we're going to take the summations. So imagine we have a graph and every single integer coordinate, so x value, so 1, 2, not coordinate, so 1, 2, 3, 4, 5, right? Let's draw some lines. And we add the height of all these together. What is that sum? Well, to do this, we could just use a summation. And it's already proven and given that the summation from x equals 1 to infinity is of 1 over x to power of a is equal to 1 over a minus 1. So if you don't know what it is, it's usually just means the first term all over 1 minus the ratio. So our ratio is 1 over a. So let's actually put our first term. Our first term when x is equal to 1, so that's 1 over a. And then our ratio is 1 over a, right? Where a is like a number, which is like, say, 5. So it's 1 over 5. So that will simplify to 1 over a, and that's a minus 1 over a. And dividing by a fraction is the same thing as multiply by reciprocal, so a or a minus 1. So cancel that from the top and bottom, you get 1 over a minus 1, right? So this is how they got that formula. So using this concept, we're going to be using this to finding the summation from x equals 1 to infinity of x divided by a to the power of x. So imagine you want to find the summation of x divided by 5 to the power of x. Like that would look like 1 over 5, 2 over 25. Since you're adding them, sorry about that, no commas. Plus 2 over 25, plus 3 over 125, plus 4 over 625, plus 5 over 3125, right? And etc. as it gets bigger, right? I mean, gets smaller, right? Because the exponential will always be increasing faster than a linear. Well, if it's like a higher base. If it's something like 2, then sometimes it might be smaller. So what we're gonna have is these numbers which we had to add together. So how do we do that? Because the number on the numerator isn't staying constant, so we can't just add numbers like that. So what we had to do is think about this like as a picture. Okay, so let's kind of make this smaller so then we could think about this later. Okay, and then this is the overarching summation that we're trying to look for. Okay, so imagine, since let's use the case for 1 x over 5 over x. So how do we write that? We have the first term, which is 1 over 5. And then the second term is 2 over 25, right? Let's split that up as 1 over 25 and 1 over 25, right? So 1 over 25 plus 1 over 25 is 2 over 25. And the next one, we put 3 in here. So that's 3 over 125. But let's split that up also as 1 over 125, 1 over 125, and 1 over 125. Okay, now let's put in x equals 4. So if x is equal to 4, that's 4 over 625. So let's split that up as 1 over 625, 1 over 625, 1 over 625, and 1 over 625. And we're going to order it like this. So as you see what we're doing, we're going to keep the numerator 1, but the denominator is changing. So as you keep seeing, as we write more terms out, this one is going to be 1 over 3125, 1 over 3125. 1 over 3, 1, oops, sorry, 3125, and 1 over 3125, 1 over 3125, right? So what are we seeing? Well, we're seeing a sequence that's multiplied by a infinite geometric sequence that's going this way, right? For each one of these sequences, right? So 1 over 5 times 1 over 5 is 1 over 25. 1 over 25 times 1 over 5 is 1 over 125, and it keeps multiplying by 1 over 5, right? Same thing case here. 1 over 25 times 1 over 5 is 1 over 25. So instead of having one sequence like this that gets this sum, we're having multiple sequences that are happening. So there are sequences that are going horizontally, which we are adding, that we need to find the sum of, but there's also a sequence going down, because we need to add this sequence with this sequence with this sequence with this sequence with this sequence, and then there's even more that I didn't write, because imagine we have more terms of x, as you see, right? So what is this pattern that we're looking at? Well, look at this. Let's look at this. The first sequence has all the terms. The second sequence has all the terms but the first term. The third sequence has all the terms except the first two, and the fourth sequence all the numbers except the first three. And the fifth sequence has all the terms except the first four. So instead of using one summations, right? Because if we're using one summations, we're working just horizontally. Since we need a horizontal and a vertical, we could use two summations, a summation inside of a summation. So how this kind of works is that, imagine we have a summation that just gets this as our number, right? So we could just write this as the usual. So infinity x equals 1. So 1 over ax. So we're just conceptually thinking about this. So this summation by itself will give us when x starts at 1 to infinity, right? So it starts at 1 and it goes to infinity. Now that sequences start at 1, but we don't want it to just start at 1, because if this one starts at 1, we're only getting this sequence. We need all these other sequences too. So we can't just set it constant as 1. So what we're going to do is that we're going to set that number as a variable. So let's call this variable n, right? And this is where our second summation is coming from, because our first summation is going to give us the sequence that's going horizontally. Our second summation is going to give us our sequence going vertically. So we're going to write that, parentheses, and we're going to have a summation outside. Okay? And now we're going to say that as n, because we put this as n. So we have a summation where this is our first sequence. So we start at the first term, then we start at the second term, then we start at the third term, then we start at the fourth, then we start at the fifth. So you're kind of seeing where we progressing down, right? So that would just be linear. So that would just be a summation by itself. So we start at n, right? So this will be the equation that we're looking at. Okay, so now instead of thinking of just x over 5 over x, we're going to think about the general case of how this works, and we're going to be deriving a formula. So all these formulas that we're going to be deriving, we're just going to brute force our way through it using summations. So as we see here, right, this makes sense, right? Because if we have a infinite series, this is just a summation. So what this regular summation does is basically we're gonna have a bunch of, let's say a bunch of these placeholders are a bunch of numbers. They're not all one. I just put it as ticks. So then we know all these place values are numbers, right? So this would be 1 over 5, this would be 1 over 25, this would be 1 over 125, and this would be 1 over 3, 125, right? And etc. And imagine this one starts at 1. So it starts at this first digit. Now, when n is equal to 1, right? So it gives us this entire summation. Now, when n is equal to, right, we start at 2, and then we give a bunch of summations. And then when n is equal to 3, we give a bunch of summations. So conceptually, when we wrote this out, this would definitely give us our entire summation. A summation inside of a summation, and which is why it works. So now we just need to simplify this. So how do we simplify it? Well, all we have to do is work from inside out. So we know what a infinite geometric summation comes out to, the summation inside, right? This is just right here. So we just need to find that summation first. So what is our first term? Well, our first term is 1 over a to the power of n, right? Because you need to plug in x is equal to n. That's our starting term right here. So we have to plug in x is equal to n. So just substitute x is equal to n right here on this variable. And then we have n. That's our first term. And then we have 1 minus 1 over the ratio. So the ratio is 1 over a. Okay, so let's simplify that. So 1 over a to the n. Don't worry, you're not going to simplify n at this stage yet. So this one will be a minus 1 over a. So that would just be a over a minus 1 times 1 over a to the power of n, right? So I just moved that denominator to the numerator, right? Dividing by fraction is multiplying by its reciprocal. So, and then I just moved that out of the numerator. So we have this. So that gives us this formula. Let's delete this part because we don't need it. Okay, so substituting this into here, we have a summation where we start n is equal to 1. So we already simplified our inner summation. Now we just need to get our outer summation, which is a over a minus 1 times 1 over a to the n. Okay, so now we have a over a minus 1. Remember, a is a constant. It's not a variable. We just have a as some kind of variable for now. So it can stand for, like, say, 1 over 5x, right? So a is going to definitely be a constant. We just need to move that outside. So a is not going to do anything. Times a summation of n is equal to 1 to infinity. And then we have 1 over a over n. Okay, so we have this. I'm going to delete everything else. If you want to record it down on a piece of paper, that's cool. But we're just going to get the formula at the end. And that's all that matters. Okay, cool. So we have a over a minus 1 times, and then the summation of this. Well, this one, again, is just another one of these. So all we have to do is just plug it in. So our first term is when n is equal to 1. So 1 over 1. A to the power 1, which is just a, right? And then we have 1 minus 1 over a. Okay, so this looks a lot nicer, right? So that equals to a over a minus 1 times 1 over a over a minus 1 over a. And let's move that down. So a over a minus 1 times dividing by a fraction is multiplying reciprocal. I'm going to keep repeating that because you're going to see this over and over again. So, but once we're going to see this pattern, we're going to stop using it. So that's just going to be 1 over a minus 1, right? Which makes sense because this summation is exactly this. So you could just substitute this in and not do all this work, but I'm showing it by all the step process. So that means our summation would just be a, right? A times 1 is a, and a minus 1 times a minus 1 is just a minus 1 squared. Okay, so that tells us that the summation from 1 to from 1 to infinity of x over a to x is just a divided by a minus 1 squared. And that is our formula for when we have a linear divided by an exponential. And you could test if this works using a calculator. You use like some rough estimations. So let's say we use um, let's say three. Oh, sorry. Let's say we're gonna use 3x divided by 5 to the power of x. Okay, so what we're gonna do with this? Well, this is still a linear. All you have to do is just say 3 times x to the power of 5 over x, right? We just distribute the 3 out. So we could just multiply 3 by whatever this number is. So we know what this is, right? If we had to put the exact value, it would just be equal to 3 times is right here. So our a is equal to 5. So it'll be 5 over 5 minus 1 squared. So that'll be 3 times 5. 5 minus 1 is 4, so 4 squared is 16. So it'll be 3 times 5, which is 15 over 16. Okay, so let's kind of use our calculator to do some like math here. So when x is equal to 1, and we put it in here, so that's just 3 over 5. So I'll just be writing this down so then you can put it in your calculator. X equals 2, so that's 6 over 25. X equals 3, that's just 9 over 125. And then x equals 4, we have 12 over 625. And x equals 5, we have 15 over 3125. I'm just following this formula, right? Just plug in some numbers. It has to be integers because we're working summations. So x equals 6, that would be 18 over 15, 1, 625. Okay, let's stop there. 6 numbers seems to be enough. And let's add all these numbers together. So 3 divided by 5 plus 6 divided by 25 plus 9 divided by 125 plus 12 divided by 625 plus 15 divided by 3125 plus 18 divided by 15625. Okay, and your number should come out at roughly, so using a 6-term estimation, because we only have 6 terms, not infinite, we have 0.937152 it, as our estimation. Now our actual answer is 15 over 16, so what does that come out to? Well, it's gonna come out as 0.9375, which makes sense, right? We see the 9, we see the 3, we see the 7. The only thing that's different is the 1, 5, 2, and the 5, which makes sense because this is going infinite, so it's gonna add more terms later on, like the 7th term, the 8th term, the 9th term, etc., right? It's gonna add all the terms to infinity, but it gets so small that it's gonna converge to this number. And that's why this is a rough estimation, which is why it's so close. So this kind of doesn't really prove it, but it shows that our formula is definitely right in a way. So this formula is what we're gonna, the idea of how we're gonna, how we got this formula, we're gonna transition over to our second video. Well, thanks for watching the first part in this video, and check out the second one if you want to find out how to do higher level polynomials.